Hey, good evening, everybody. I hope everyone's having a wonderful day. If I sound any funny today, or I make any weird abominations, whether it be snot or anything of this nature, I apologize in advance. So if I make any weird noises, hopefully you don't mind too much. I'm doing my best today. So, anyways, today is the last lecture for the course. So today we're going to be finishing up talking about 2-4 trees, and then we're going to talk about B trees, which are our final data structure for the course. So before we get to the B trees, I want to talk about the removal. We got to talk about how do we do these removals. So last day, I introduced you to the idea of how we could do these two kinds of operations. The whole idea is about borrowing records from siblings. If there's enough to go around with a sibling, as in there's enough records in one of my siblings, what I could do is one of two things. One, if I don't have enough in any of my siblings, I could fuse together. I could take a record from my parent and my sibling, and I could fuse them together into a node, into the one node that is a one node, so it doesn't underflow anymore. Or if I have enough to go around, as in my sibling has lots and lots of toys or lots of records, I can always perform a transfer operation. And here's the catch that I didn't have a chance to tell you last day, is that the transfer operation is our best friend. If we can do the transfer operation, we're done. You might ask why? Why would that be the case? Is because when I do the transfer operation, the reason why I did is because I had a sibling. And if I do the transfer, that one node, the node that I borrowed one from, well, it doesn't underflow if I do perform this operation, right? So my sibling isn't affected, or it doesn't get caused. Sorry, I'm getting very excited here. It doesn't underflow. So I fix it so that now my one node is now at least a two node. So that one don't underflow. So that being said, I could just keep doing this process, but I don't have to do any more in a transfer operation. And that's why. It's because in that operation, I'm preserving that all the nodes affected aren't going to underflow. However, fusion operations can cause more issues, just like our split operation. So just be mindful of this. So I thought we would do an example. Let me just make one quick thing here. I sort of missed one thing. One thing I'll note here is that it's better probably to look at the pseudocode in the notes. For this one, I had to write it a little bit smaller on the board here for the pseudocode for remove. But we'll go through the analysis after we do our example here. So, anyways, we're going to try removing 9 from this 2-4 tree. Now, notice that 9 is not in one of my nodes that are close to the leaves, right? So what did we say we would do if that occurs? Well, what's a very natural thing for me to do? I could get the successor, right? And I could copy that into the appropriate spot. So what I could do is I could take, so if I'm going to remove 9, I can take my record with 10, because that's the successor, right? I could just go to my next immediate child. I could go commute smallest. I get 10. I'm going to put that right here. And then I'm going to delete this, right? So if I do that, suppose that I'm at this node, right? That's the node that I'd perform the deletion at. Is this node okay? Does this overflow or does it underflow? It underflows. So we need to do something about that, right? So notice that in this case, notice that if I have a sibling, look, I have a sibling. There's one right here. Notice it's a 3 node. That means it has 2 records in it. So it means that I can always perform what kind of operation here? What kind of operation should I apply to cause this node to not underflow anymore. So what's the name of the operation? A transfer operation. Very good. So I'm just going to do a transfer operation. I'm going to bring 16 up, and I'm going to pull 15 down. So 15 comes down here. 16 comes up here. And now, well, let's see. Well, now this one isn't underflowing, so let's consider its parent. Does the node with 16 in it, does that underflow at all? No, right? So we're done the removal. Sorry, I sound a little bit funny here today. So let's do another example. So let's now, instead of 9, let's now remove. Let's remove 17. Let's try removing 17. So 17's right here. So one thing I'll tell you up front is that whenever I am at a node that isn't among the parents of the bottommost level, the ones that are right beside the leaf nodes, you know that right away you're going to have it where you're just going to replace whatever it is with the successor. If I'm at this level where any one of mine are leaf nodes, this is what I said about why I told you that the removals are much easier to define for the 2-4 tree, is that if my children, if any one of the children is a leaf node, you know you're right down here at the bottom of the tree, right? If it's not the case, then you know you have to replace it with the successor. Does everybody see that? So there is very little wiggle room for how we can do this now. So it's actually much easier for us to define the removal operation rather than our much more loosey-goosey kind of way we had with the multi-way search tree more broadly. So now we know if we need to replace it with the successor, we know that we're talking about nodes up here, right? Not ones down here. Here we could just simply pull it right out and kill off one of the children. But let's be gentle. Let's not actually kill any children, okay? I had to do that today. Not me. I'm just being goofy. So, anyways, I'm talking about these children, by the way, not actual children. Nobody has been harmed by this lecture. So let's proceed. So, 17, it's right here. So if I get rid of this, so I don't have to replace with a successor or anything, I'm at the level just above the leaf nodes. So I just get rid of this. This node, does it overflow? Does it underflow? Or is it okay? It underflows, right? But now notice that this node, my only sibling. So just to make this easier for us to see, I'm going to call this one V. This is V's parent, and this is W. So this is my only sibling that I have out of all of them. Now, if I had multiple siblings, say one right here and one to my immediate, because remember, I'm talking about my siblings here. They have to be to my left or to my right of me. Otherwise, I might destroy some sort of the properties of my tree, right? So if this is my only one here, right? What kind of operation do I need to do? Because surely my sibling here doesn't have enough toys to go around, right? There's not enough records there. So what operation should I do? Yeah, fusion. So what I'm going to do now is I'm going to take this. I'm going to take out this record and I'm going to fuse them together into my node here. I'm going to take these. I'm just going to fuse this all together now. I'm just going to fuse them together. So I'm going to take the 16, the 15. I'm going to fuse these together into one super node. And then there is my fused node. Now, question. So now I consider, say, my parent now. Because this is most certainly not going to underflow anymore. Is V overflow, underflow? What's going on here? In this case, it's underflow. What operation should I apply? Yeah, transfer operation. Very good. So just if you're not catching on what the transfer does, I'm going to pick the 5. I'm going to bring it up here. And I'm going to bring down that 10. I like to think of it just like the rotate operation. It's a very intuitive way of viewing it, but it isn't literally the same, but it's very similar. It's a very similar thing going on there. That is not a coincidence. So if I bring down the 10, notice that if I do this operation, so let me see here. What do we got here? So I have, so if I take this 5, this 5 is coming up. 5's coming up, 10's coming down. But now you might ask, okay, so what happens to this one right here? Quite like the rotate operation, there's going to be an exchange that happens. A transfer of sorts, right? So just be very mindful of the fact when a transfer operation happens, you're also going to be handing over whatever the child is to your right. In this case, if it's to the right, if it's to the left, you'd be handing off whatever's on this side over to the left. So just like a rotate operation. So this should remind you a little bit of a rotation. So in this case, if I go now up to root, am I doing okay? Is this is perfectly fine, right? That doesn't underflow, right? Is there anything else I have to do? I think we're doing okay. I think we're doing okay. That should complete the removal. So just note that we do the removal. So after I remove 10, so I didn't remove 10, I just transferred it down to here because remember this node was underflowing, but I had a sibling. This sibling here, like if I give it a name like W, see at that time it was V. But I had a sibling that had more than enough records so that if I took one from this one and put it up here, I could bring this down to preserve the ordering of the tree. If I do this, I can make this not underflow anymore, but when I do this transfer operation, one comes up, the other one comes down. I take and move whatever's here into the parent, then I take whatever this is between my two children, I bring that down. But the point is, when I do this, notice that I have to give this child that used to be right here and make that now to the left that fulfills the other child that otherwise wouldn't be there. Because it used to underflow, right? So now it's a 2 node as opposed to a 1 node. So I thought it would be a good idea for me to just give you a quick summary of the remove algorithm. We'll do the analysis quickly. So I must stress, I have the pseudocode in the notes, but if you understand the idea, you pretty much may as well not even need this pseudocode. But I encourage you to take a look at it in the notes. But here we go. I'm going to walk through what we did. So just think of this more as a review of what we just did. So the first thing is I find the node that contains the key that I want to remove, right? So I remove that, and if needed, I replace it with the successor. So we did that actually in one of these operations that I did, right? So if I need to do that, there's going to be a node that I'm just going to reassign to be, in our case, V. So you might ask, okay, so what happens after this? So I do a find, I remove it, and then I have to go through this process of fixing up any underflows that might happen. So while node V, so remember I start down here and I worked my way up the tree. So if V is the root, then you just make whatever V's first child is the new root. Because it's possible that when I do a removal, if it underflows, it might be the case that I might have to update something to be the new root. Because I might actually you know how I talked last day about how when I do the insertions, when I do put operations, it grows the tree upwards like this. When I do removals, it shrinks down and diminishes like this, and it starts collapsing in. So this is actually why this case is here. So otherwise, if we have a sibling with at least the ceiling of D over 2 keys, now you might ask, why the ceiling of D over Q? Now remember, in a 2-4 tree, D is 4, so the ceiling of 4 over 2 is just 2. So what this is really just saying is that if you have a sibling with at least 2 keys in it, meaning it has 2 records, it says that you can do the transfer operation. You do it with W, like I labeled here, like W. You would have V and its parent, and you perform the transfer operation in this case. The reason why I wrote it with D in here is because what we're going to be seeing is that these algorithms entirely generalize to the next data structure I'm going to show you. So I won't actually have to ever write out what the removal for the B tree is, for example. Its algorithm is the exact same. It's just that the concept's going to generalize. So that's what I mean by D here. So remember, in our 2-4 tree, D is 4. So if you're taking a look at the pseudocode afterwards, just note that D is 4. I think I even mentioned it in the notes. So we have that. And now if we don't have any siblings we can borrow from, that's when we do the fusion operation. So we do it with W, which would be where I need to fuse whatever's with that node, with whatever the parent, and also with V. I fuse them together in this case. And then I go up the tree, right? I go up to my parent. And then I continue doing this process until it's no longer the case that it underflows. So you might ask, Dad, what is the time complexity of all of this? So let's walk through this. So first, finding a node. Finding the node we established takes big O of H log D. Then next, this whole removal process where I find the successor in it, all of this I could do in big O of D plus H log D. So this is all stuff we established in previous lectures. I'm just going to substitute what H and D are in a moment. Then I have what's going on with this. So in all of these cases, you'll notice that when I update what the root is, or all of these, any one of these cases, if you take a careful look at the transfer operation or the fusion operation, we always evaluate a constant number of nodes. There's always a constant number of nodes, and we do manipulations of the data in a constant number of nodes. But how much data is in each one of these nodes? Well, something like big O of D, right? So it means that if I have a constant number of nodes that get affected, where each of them, when I do a manipulation, takes big O of D, then it all takes big O of D, right? So this is true for all 3 of these cases. Sorry, down all the way down there. So this takes big O of D here. But I have this while loop. So it's possible that I have to go all the way up the tree, just like in my example here. Notice that I went all the way up to the top of the tree. Now, so I went all the way up to the root. So in this case, you know that it's going to be most certainly, at most, the height, right? That I'm going to have to deal with in terms of big O. So I'm going to have big O of HD again. So I have big O of H log D. I got big O of D plus H log D. And I have big O of HD. So notice that I have D plus a H log D. This is log D. The most dominant of all of these is going to be HD here. So we know that the time complexity for the removal, because, so as H is big O of log N, and D is equal to 4, it is big O of log N. So that means that for insertions and removals, we can all do these in log n time, just like with our AVL tree. Isn't that fascinating? So in some aspects, you can almost look at this generalization, and you can say, hey, look, it has the nice same asymptotic results. So before we proceed, are there any questions about what we just did? So this is just saying, so when I have V is assigned to be the parent of V, all I'm saying is you're going up to the parent and you're going to apply the same process again. So that's why, notice it says while node V underflows. So I'm just at this step because remember, if a fusion happens, I may be causing more underflows to happen. The transfer is the one that's the sure dandy one that'll make sure we don't have any more underflows that happen. But if this occurs, I'm going to have to go to my parent and I'm going to have to see if it underflows there too. If it underflows, then I'm going to have to proceed with this process again. So that's all it's saying. It's just like when we had the AVL tree, when we had to go up we walked back up the tree. This is quite similar to this process where we go down first to find the node we need to remove. This process right here is very much the same idea. It's the same idea. We just walk back up the tree. But there's a point where we can actually stop if we get a transfer operation, which is rather nice. At least that's my opinion on it, is that it makes it kind of nice. So, anyways, if there aren't any more questions about this, the main reason why I wanted to show you the 2-4 tree is because notice that we can still get the big O of log n for our insertions and removals. We can do all of the algorithms we had before because we know that the height is big O of log n. For the 2-4 tree, we can get all of those operations still, even with this much more general family of search trees. Is that neat? So you might ask, Dad, where are you going with this? Well, I'm going to make it even more general. So that I thought would be a perfect way to end this course, is to show you probably one of the more complicated looking search trees, but it actually follows the exact same principles we just talked about. So if you understand the transfer operation, the fusion, and also the split operation, they're not going to change. It's just that I'm going to impose a new definition of what underflow and overflow mean. So let's talk about our final data structure. We're going to talk about the B tree. So I thought this would be a perfect place for me to stop for this course because, one, if you say, for example, are interested in, for example, databases or data generally, a lot of the underlying data structures that make a lot of these technologies work a lot of them are based off B trees. So if you're wondering yourself like, oh, why would you want to talk about these? That's one reason why. File systems, a lot of them use variants of these B trees, so-called B plus trees, for example. We'll talk more about this after we talk about how the B tree works. That'll be what motivating the last application I'm going to show you. So here we go. So the first thing I want to mention is this is from 1970 by Bayer and McCreight. And I'm going to give you this, the main reason why I want to show you this data structure. It's a little bit different than a lot of them, but it's, but I want to mention that B trees belong to the best node data structures for maintaining data structures in external memory. Because very often we've been talking about data structures where we have them all loaded up into memory and we manipulate them during runtime. So I thought it would be important I show you at least one data structure that has a nice application for external memory. So things you can save off in a file, for example, that you can load up again. So keep in mind, you can do that with all the data structures we talked about, but I think this one is it's an interesting one. So you're going to see why when we get to the end of this lecture. So we're going to talk more about that later. So here's the definition of a B tree. So it's just a multi-way search tree. So it's a multi-way search tree. T with order D So its order is going to be D. That means that all of the children are going to be at most. So if I give you any one of the nodes, the number of children it has is going to be at most D. Such that we have the following properties. Such that, here's the first one. The root of T has at least 2 children and at most D children. 2, so that's the first property. The second one is the number of children. The number of children every internal node must have is at least the ceiling of D over 2 and at most D. And finally, the third property, it should remind you a lot of the 2-4 tree, but believe it or not, it's really buried in this definition, is it satisfies the depth property. So it satisfies the depth property. So if you don't recall that from last day, it's just simply that all leaf nodes are at the same level of T. Now you might say, Dad, what the heck is this? Like ceilings of D's over 2? Like, what is this? What is this? This is strange. So let's think about this. So I want you to think carefully about what this definition actually is really like if you think about it in terms of the 2-4 tree. So I want you to look at this definition and plug in when D is equal to 4. So let's see. The root has at least 2 children, and it means at most 4 children. We know that is true for the 2-4 tree, right? It has a 2-node, 3-node, or a 4-node. The number of children of every internal node must have at least the ceiling of D over 2 and at most D for its children. So if you plug in 4 in here, it's at least 2 and at most 4, right? So notice that these all collapse into the 2-4 tree if you plug in D is equal to 4. So everything I've told you about 2-4 trees are actually just a special case of this data structure. So spoilers. So everything I've told you about 2-4 trees is just as true for the B tree, with one exception. So the algorithms I showed you, we're going to just need to redefine a couple of things, what underflow, overflow is, and what the height is. Because the height we proved was heavily reliant on the size property and the depth property. So just to give you a clear idea what one of these would look like, so if you have D is equal to 4, you get the 2-4 tree. So just to be very clear, the B tree generalizes over the 2-4 tree. So it means that this is an even wider family than the 2-4 tree, and it's even more wider than even other search tree families. So it's like I said, it captures a lot of different kinds of search trees. So let's talk about this. So I first should maybe draw a picture of what one of these might look like. So one thing I do want to be very careful about is, remember how I said that we think very often about that D as like a parameter that we have control over. It's very intuitive for the B tree to have it that way, so that we can control what D is. So you'll find that when we get to the application towards the end of the lecture, you'll see that I'll actually have a very ideal way of picking what D should be for a given application. So everything I'm going to tell you, you could use like, the algorithms all work even if you don't pick a D specifically. But most certainly, there's going to be some applications where choosing D appropriately actually leads to really nice performance results. So I'm hoping it'll be like the Grand Poobah to show you what I mean by this. They'll show you some pretty interesting results when you pick the appropriate D. So I thought I would draw you a picture, just so you can see what one of these might look like. So I'm going to have the root be 30. I don't know how wide I should be actually drawing this, because as you might notice, the B tree is rather, it's like I said, it can have quite a broad structure to it. So 11, 21, 35, 42, 50. Now let's hope and cross our fingers I made enough space for all of these. Okay, I think we're doing okay so far. Oh man, this one's gonna get a little crunched. I'm gonna move it over a little bit. Just gonna make a little bit more room for myself here. And this will be much better. I better draw in all these leaf nodes. There's gonna be a lot of leaf nodes. One, two, three. This next one has 4 of them. Did I? Let's see. That one has 5. Let's see. 1, 2, 3, 4, 5. This one, I think, only actually has 3 in it. Yeah, this only has 3 in it. My apologies. It only has 3 leaf nodes. Then this one has 4. My apologies. Then this one has 3. Then this one has 3. So let me just fill in the keys. So 5. So I'm going to do it across this level. So I'm going to have 5, 7, 13, 13, 16. I'm going to have 22, 24, 26, 29. Oh yeah, missing. There is actually another leaf node in here. Let me just make some more space here. 29, 32, 34, 36. Yeah, because, yeah, this one definitely has 4. So 36, yeah, 36, 37. So 36, 37, 39. I kind of dripped it down there. It's kind of melted down. It's perfectly par for the course. 36, 37, 39. 44. 49. Then 55, 56. Okay. So here's a B tree. So this is an example of a B tree. Now, can somebody tell me what the order of this B tree is? What's the order of this B tree? So just think of the node that has the largest number of children. How many children does it have? So notice that this one has 2, that has 3, this one has 4, this one has 3, this one has 3, this one has 5, that has 3, that has 4, that has 3, that has 3 over there. It's 5. Yeah, its order is 5. So this is the B tree of order 5. So one thing to just be careful about is, remember, it has 3 properties. So for example, if I were to remove 5 from here, and I put it like this, like suppose that I just remove 5. Is it still a B tree if I do this? So let's think about it. So let's look at the definition. So the first thing is that the root has at least 2 children and at most D children. So somebody's asking, how do you figure out the order? You figure out the maximum number of children of any one node in the tree. So in this case, there is a node that has 5 children. So that's the largest number of children any one node has in this tree. So the order is 5. It's a good question. No, anytime. So somebody suggests yes. Well, let's think about the definition. So the root's okay. Property number 2 says the number of children of every internal node must have at least the ceiling of D over 2 children and at most D. So let's see. So what's the ceiling of D over 2? Well, here it's 5, right? So it's 5 over 2. 5 over 2 without rounding it up is 2.5, right? Well, it's 3, right? But this right here is definitely bigger than having 2 children, right? So if I were to get rid of 5, I would have only 2 children on this one node, and I would have a 2 node, which would mean it's not a B tree if that's the case. So just be mindful of the fact that the internal nodes, so there's like the root has a property, the internal nodes also have a property. So in this case, we can't have it where it has too few records in a node. So the order of the tree is actually intricately tied to knowing if it satisfies the definition or not. It's a wonderful question, by the way. So as I just want to remind you, remember, the B tree is just a generalization. So what's D? It's the order of the tree, which you could think of as, so what's wrong with removing 5? Because it's a 2 node, I require that it's actually a 3 node at least. In this case, if the order is 5. That's property number 2 in the definition. That's why. But yeah, D is the order of the nodes. So the nodes are not, so D is, you can think of it as a parameter, or you can let it freely mutate in the tree. In the B tree, it's very useful to think of it as a number that I get to pick, but all the algorithms will work regardless if I let D be whatever. But the thing is that once I commit to a D, I have to stick with it. But you can just think of it as a parameter that I have control over. So if I want to decide that D is 20 or D is 100, that's okay. So as I mentioned, if you had D, so remember the order is 5, so that means D is equal to 5 for this tree. So if D is equal to 5, that means that every one of the internal nodes has to have at least the ceiling of D over 2 children. If I don't include 5 in this node, it has 2 children. That's too little. I require 3 or more in every one of the internal nodes. That's why. So, there's a few things I want to bring up that are really important for the discussion for this. Now, you can use an argument similar to the one I gave you for the 2-4 trees to prove that a B tree, so a B tree has height big O of log base D of n. So the other fun catch is that all the algorithms for the 2-4 trees are no different. So my apologies. Are no different for the B tree, except we use more general definitions. More general definitions. So I'm going to give you these definitions. So, namely, as I suggested earlier, is I'm going to redefine what underflow and overflow mean. So, can anybody tell me, What does it mean for a 2-4 tree to overflow? Can somebody tell me what does it mean for a node to overflow in a 2-4 tree? What kind of node is it? So is it like a 3 node? Is it like a 4 node? It's a 5 node. Exactly. Exactly. It has 5 or more children, right? So if I get a 5 node, the node's too fat, and I'm going to have to do a split operation, for example, if it overflows. So I do splits when I do insertions. Like, I mean like a split operation, not me. Like, listen, I haven't done a split in years, okay? So the point is that I'm going to come up with new definitions for these, and they're going to fall perfectly in line with the algorithms I gave you last day and today. I'm just going to redefine them. Rather than being a 5 node for the overflow, can somebody tell me, by the way, for underflow, what kind of node did it become? Was it like a 2 node, a 3 node? Like, what kind of node was it when it underflows? It has less than 2 children, right? It becomes a 1 node. Means it has no records in it anymore. So we had to do some borrowing. So let's redefine these for the B tree. And you're going to see that all these are just generalizations of the same idea. A node overflows if it becomes a D+1 node. So that's what overflows means for a B tree. If you actually just plug in D is equal to 4, like our 2-4 tree, you'll see it's exactly the same as we had for our 2-4 tree. Why? Because it's a 5 node, right? When it overflows. Now I'm going to give you the definition for an underflow. A node underflows if it becomes a, now this one's going to be a little bit stranger. This definition is really nice and natural, right? But you got to remember that the bound that we had for the number of children is at least D over 2, the ceiling, right? So if I get any less than this, you know that you're going to be in trouble, right? So that's how I'm going to define underflow. It becomes the ceiling of D over 2 minus 1 node. So it becomes the ceiling of D over 2 minus 1 node. So it just becomes a node where it's no longer satisfying the lower bound of the number of children. The one that we had in property number 2 for the B tree. My apologies, I'm getting very worked up here. Now here's the neat part. Did you notice that in the algorithm I gave you just earlier, and even the one I gave you last day, all they relied on was having the definition of an overflow, underflow, and something about D over 2 keys, right? So that means that you could literally just use the same algorithms I just gave you for the B tree, just if you use these 2 definitions for overflow and underflow. So I thought maybe I'll show you an example of what I mean, but if you find yourself curious about this, I'll let you take a look at the notes. To be very clear, I'm not going to test you on insertions and removals for B trees on the exam. So don't expect me to test you on that. 2-4 trees, that's fair game, but not the B tree. The B tree is a little bit, I don't know, there's enough fun drawings today. So I'll just keep it a little bit easier for us when it comes to this. So anyways, I thought we'd do an example just to illustrate what I mean by the power of our ideas. So this comes in the same theming of what I've been talking about the last few lectures. You know how we've been taking ideas and patterns that we've been thinking about for solving problems, right? But we're adapting those for data structures. So notice that every single time I've been trying to find a pattern in a way I can try to solve a problem. But remember, I'm trying to represent a data structure that resolves the dictionary problem, right? So I'm just looking for patterns that I find useful. For example, when I do the searches, remember when we did the binary search trees, we're trying to take advantage of the pattern that we see for binary search, right? But the whole idea there was I needed to make sure I rebalanced the tree to make sure that its height is logarithmic, right? So I've just been taking these ideas and building on top of them. Isn't that natural? It's a really interesting idea. I'm hoping that you maybe look at this and be like, that's actually kind of interesting. Like that just seemed like it just sort of organically happened. And this is one of the great things I really like about computer science is that when you look at algorithms or data structures and when you talk about problem solving, you very often will find that sometimes you could come across a problem if you study it carefully enough. Sometimes it reveals itself some interesting property. In this case, the B tree, for example, its height is rather useful for us. So if we can maintain or use that, that's our best friend. So I thought, just to illustrate the power of extending ideas like this, I thought I'd show you how we can do an insertion in the B tree. So I'm going to use this same exact tree. I'm going to insert 25 into it. Now, I will tell you up front, the reason why I like to do the B tree last is because the data structure just looks like a nightmare. But it's really organized, believe it or not. That's just me just being a little bit more complainy, having a good time with this. So if I do insert 25, you actually know the algorithm for this. So first, can somebody tell me which node should it go in? Which one? So can somebody tell me the keys of the node that 25 should go in? So I see somebody suggesting left 3. So yeah, the 22, 24, 26, 29, that's where it should go, right? And you know how to do this, right? Is that wonderful? So I'm just going to put 25 in. So I'm going to try cramming it in here. So 25 is going to go somewhere in here. It's going to have another leaf node I'm going to add in here. And true muffin top fashion, it's going to overflow, right? So you might ask, okay, so how does this work with the B tree? Before we had it where you kind of split it where one becomes a 3 node, the other one was a 2 node. Well, what's going to happen when this occurs is you're going to have it where it's going to cut right down the middle, just again like before. But you're going to notice that I'm going to make sure I do it so that I maintain property number 2. So when I do this, I'm going to do a split operation, but I'm going to bring 25 up because it's right about the middle, right? So I'm just going to do my split operation. So I do the split operation. So I'm going to bring this 25 up out of here, and I'm going to split this into 2 separate nodes. So I'm going to take the 25. I apologize for how cramped this picture is, by the way. It's a really nice picture in my notes, I swear. So 26, 29, they're going to kind of kick around on their own. They're both going to become 3 nodes. 25 comes up here. So the 22, 24 goes right here. Then I have 25. 25 is going to get the 26 and 29 right here. So the question is, do we need to do anything else? Does this node overflow? No, right? Because it's, look, remember our definition. It says it overflows in this case because the order of the tree is 5. That means that it would have to be a 6 node, but we're okay now. So we're done the insertion. So do you see how all we're doing is the same exercise again, except I just redefine what overflow and underflow are. Does everybody see that? Is that fascinating? So we're talking about this really general data structure, but really we're just adapting the same ideas that we've been taking from our earlier lectures. I just think that's amazing. I don't know what you think, but I think that's pretty exciting. So you might ask, okay, so what do you mean by all this stuff? Like this just doesn't seem very, all I've done here is I'm just generalizing these ideas. You might ask, okay, what else can you do with these B trees? So I'll let you take a look in your own time about how the removal might look. But I will stress, I'm not going to ask you on the exam at all to do insertions or removals for B trees. Just to be very clear. Because they would be an absolute nightmare to draw on an exam. Because I expect you to not have to worry about that kind of hassle on an exam. But anyways, are there any questions about what a B tree is before I try to justify why we might call the B tree a B tree? Which sounds kind of funny because you think, oh, well, like it's just called that, right? But actually, there's some suggestions of why it might be called that. And I'm hoping to convince you that maybe, possibly, it has a specific name because of one of its killer applications. Okay, so it's 2-4 because we could just have a minimum of 2, maximum 4. Correct. So remember the 2-4 tree? We only are allowed to have 3 different kinds of nodes. A 2-node, a 3-node, and the 4-node, right? We're only allowed to have nodes. So all of our internal nodes either have 2 children, 3 children, or 4 children. And remember, each of these might potentially be other internal nodes. But remember, because of the depth property, all of the leaf nodes are at the same level. So everything I said about insertions with the 2-4 tree, how pretty it grows like a flower, the B tree has this property as well. So I just think it's kind of fascinating. So anyways, I want to talk about why would we be interested in these B trees? Because, we've talked about searching, sorting, all sorts of different things. And I brought up this thing about external memory. So I thought I would dedicate the rest of the lecture to talk about this. So let's talk about why we might consider a B tree. So let's talk about this. Let's talk about the B tree. So why would we consider a B tree? So we're going to see. We're going to see what this is. What perk do we get out of the B tree? So one tip I'll give you, just something you can keep in the back of your mind, is the height. Is the height of the B tree. So why consider B trees? So why B trees? So computers have a memory hierarchy. So this is something you may have encountered if you've taken a systems class, is that memory itself is that memory takes the form of a hierarchy. And you might know that hierarchies are very natural for modeling trees, right? So if I want to have a hierarchy, one natural way on a computer to represent a hierarchy is with a tree. So, a memory hierarchy, each level varying in size and our subdistance from the central processing unit, from the CPU. So, just for the sake of simplicity, I'll just refer to the CPU as a single unit. So, you might ask, okay, so what do you mean by all of this? So I'm going to draw you a picture. I'm going to explain this picture to you because I'm not even kidding. If you've never taken a systems class, you're going to find that some levels of this hierarchy are going to be more relevant to some of your future courses. Other ones, maybe not so much. But you're going to find that if you're interested in lower level memory manipulations or higher level, knowing about this hierarchy is going to be your best friend. So first we have our CPU. Then we have our next category of memory. And I'm trying to keep them in rough scale-ish, but it's not really that accurate for magnitude-wise. It's just more about the distance they are from the CPU. So we're going to have ourselves the CPU. I'm going to have volatile memory. So this is the memory that when you turn on your computer and you turn it off, this is all your active memory. The stuff that when you load up your programs and you terminate your programs, it all is in here. The stuff that's actively being used by your programs while during executing. So the lowest of leveled stuff that's closest to the CPU are your internal and so the CPU can have internal registers, then there's external ones. So you have your registers. So if you take in a class, say, for example, or you may take a class that involves assembly, for example, yeah, this is your best friend. This is like your RAM. Exactly. So you have your registers. So if you've taken it, or if you take a class that involves assembly, you're working at this level most of the time. You're working at register level where you have basic instructions, where you're manipulating registers. So you have registers, then between your registers and the main memory, which you think of as the RAM, you have your cache. So you may have multiple caches. So those are to speed up the operations that happen between the registers and loading things from main memory. So if you're thinking of main memory, this is what I'm talking about when I refer to RAM. At least if you think about memory. So if you think about RAM, that's what main memory is for what I'm referring to. So I have main memory. Notice that the boxes are getting sequentially bigger. And then I'm going to have this big box. It's going to be my persistent memory. So persistent memory, this accumulates all of the stuff I store, say on a hard drive or say my fancy solid state drive or something like that. This is the stuff that you hang on to when your computer turns off or you decide to save one of your files. So this is your external memory. But yeah, you're going to learn, if you've taken some systems classes, you're going to take some systems classes, you'll learn a lot about the relationship between this part and the CPU and the relationship this will have possibly with the persistent memory. Usually there's a lot of interesting computer science related issues around registers, caches, and the main memory. You learn a lot of that kind of stuff in, say, an operating systems course. It's actually a very fascinating subject in its own right. A lot of beautiful, but also systems-y stuff. So I have the external memory. So for example, this could be a hard disk. So this is what I'm referring to as the memory hierarchy. So you might ask, okay, so Dan, I probably know already about this, possibly. But if you don't, here's the thing I really want you to be aware of, is as I go further and further away from the CPU, the amount of memory I can have seems to get bigger. So notice that the scale of how much memory I have gets bigger as I get closer and closer to persistent memory. This is sometimes due to just technological limitations. Other reasons why it's because it's cheaper. But here's the other thing. The closer you get to the CPU, the faster memory acquisitions are. So faster you can perform operations that require memory accesses. So for example, if I have something in main memory, it maybe has to get loaded based on the cache into the registers, that gets passed along to the CPU on an instruction fetch, for example. I'm not going to get too much into the details here. That's more appropriate for a systems course to address. But the point is as you get further and further away from the CPU, specifically when you get to external memory, it may be the case that those memory acquisitions, those memory requests, they get expensive, especially if you're using an older style form of memory. So you might be like, oh, Dad, that's a wonderful. I have my solid state drive. It can load things up really nice. Well, what if it's just a disk drive, like a hard disk? Well, it might take a little bit longer due to physical limitations, but regardless, it follows the same pattern. So this is the idea of the memory hierarchy. Are there any questions before I proceed? So I'm going to show you how I can use the B tree to try to work around this stuff. And I'm not saying work around like I'm cheating or anything. It's just more about the issue that I've just presented to you, is that if I want to access things from external memory, that's going to be expensive. So I would like to minimize the number of accesses I require to load things from external memory. So what are caches? You can talk to me after class, okay? I just want to make sure I give you an idea about just the overall layout of these. But I can talk to you about after class, okay? I do appreciate the question. I do have more details, by the way, in the notes if you find yourself curious about some of these details. But I do actually appreciate that question. So let's talk about the issue at hand. So suppose that I want to save or store things in external memory. So I want to come back to it later, or maybe I'm storing it in some server somewhere. And I want to, or even on my own computer. Like say I have a file system tree, for example, and I want to load up a part of my system. I want to be able to do this with as few memory requirements or requests as possible. So anyways, let's take a look at what we can do with this. So we're going to be addressing the problem of minimizing the number of disk accesses. So let's take a look at this. So the first thing I really want to touch upon is that B trees are ideal for maintaining large collections of data that do not fit into main memory. That's the first thing I want you to be aware of. I want to explain why. So consider the problem. Of maintaining a data structure where external memory is divided into blocks called disk blocks. And to obtain data from a disk block, requires its transfer from external memory and main memory. So where you have your RAM. So you might know this under a couple of different names. You might know this as a data transfer or simply I/O. So I'm not going to get into the details about virtual versus not here. I'm just going to keep things as simple as possible here because this can turn into one giant rabbit hole. But the point is I'm going to have these disk blocks that I'm going to request. And the point is I'm going to maintain some data structure in external memory that I want to fetch parts of it using these so-called transfers. So I want to perform these transfers, but I'm going to have to, each one of them is a request that I'm going to have to make. So this is a disk transfer. So we want to minimize the number of disk transfers needed to perform updates on our collection of data. Now, the first thing I really want to hammer in is, remember the dictionary, like the dictionary problem we've been studying for a good portion of this course, is a very natural analog for a database. So if I've told you up to this point that, oh yeah, you can have a B tree, the B tree can do the dictionary operations and all that, I've essentially been giving you a lot of the bits and pieces that naturally beget me to talk about this issue. So here's the thing. When you have things in external memory, you can use a lot larger magnitudes of data, right? Especially these days where we can have magnitudes upon magnitudes of data stored in all sorts of places. I can have several hard drives all hooked up to one computer with terabytes of data, right? So suppose we have a collection. Suppose we have a collection of 10 to the 10. So just for those that can't recall their magnitudes, this is 10 billion. That's a lot. 10 billion records. So I want to show you the versatility of the B tree. So first I'm going to show you what happens if I use an AVL tree to do this, and then I'll show you what I could do with the B tree. So let's first talk about this. So you might ask, Dan, how would you talk about a B tree like this versus an AVL tree? So the first thing you might say is that so let's first consider the AVL tree, because we know that the AVL tree has these log n operations for all of the things we've been really interested in. So the AVL tree. Let's consider an AVL tree where data is stored in each node is stored in external memory, assuming its data fits in a block. So I must stress that if it doesn't fit in a block, you may have to perform several memory requests, where you have to fetch multiple blocks to acquire the entire node. So I'm just going to make this presumption that it fits in a block for the ease of things, but if you did not have that, you would actually have to request several blocks, and you would load up the node by collecting them all up. So I'm not getting into the specifics of how that's done. That's more of something you'd see more in a systems-related course. I'm just trying to give you an idea that you can have this stored somewhere in some file. You can even just imagine it just like a file just sitting in a system, like an external hard drive or something. So suppose I have this. So what I'm saying is, you can imagine you have like an AVL tree, where each one of the nodes is kind of just sitting around here. So suppose I have like an AVL tree. I don't know, there's maybe more down here. The point is that parts of it might be stored in blocks, but it fits in a block. The whole point is that I'm going to be storing this tree in external memory somehow. There's many ways you could do that. For example, you could do a traversal of the tree and save that in a file. So what I'm saying is we're going to do this with an AVL tree. And now, one thing I want you to notice, so here's the observation. So if I want to retrieve data from this tree, notice that at worst, if a node fills up the entire block, I'm going to have to access each one of the nodes and load that in as I go down the tree to discover more of it. Because I'll have to load up a block, I'll request a block. One of my disk transfers, I'm going to need to do one for each time I get to a node. So the memory accesses, these disk transfers, how many could happen? What is it related to? It's the disk accesses actually relate to the height. They relate to the height. So remember, we know that the height of an AVL tree is log base 2 of n in big O. So that means that if I have 10 billion records, if I had this, to search for some key in this tree, I would have to potentially require, I'm going to have to go down this tree all the way down, down, all the way down, possibly in relation to the height, which we know is big O of log base 2 of n, right? But if it's 10 to the power of 10, I've worked out the calculation for us. So this will be approximately, for our example, this is going to be approximately log base 2 of 10 to the 10, which if you work this out, is approximately 33 disk accesses. If you were to attempt to do this. So this can be especially costly because external memory, accessing things from external memory from the scale that we're talking about. So I want to quickly, rapidly put together these operations. I want them to be very fast. So especially if we're talking about things that I might need for vital operations of the computer, 33 might be rather expensive. So let's see what happens with the B tree. So let's see what happens. So now, first thing I need to point out to you is that the B tree is rather versatile. I have control over D, so I can pick D so that it matches my given example. Or I can even match it to the appropriate size for my system, based on the size of blocks for my transfers. So what can I do with the B tree? So what about the B tree? So what about the B tree? So what I can do is I can choose D appropriately. So I'm going to pick D so that the data required to store the node of a tree fits into a block. So what do I mean by this? We're going to store the references to each one of the children and then the records. So I want to be able to fit that all into a data block, so I'm going to pick D to reflect this. So you might ask, what you're going to do is I'm going to imagine, I'm going to do the following. I'm going to let D be such that it is big O of capital B, where B, capital B, is the number of elements or records, number of elements in a block. For example, if we have a B tree of order D is equal to 10 to the power of 3, then that means it has 999 keys and 1,000 children per node, with my given example here. And remember, because of the selection of D, notice that D is actually a part of the height. And its height is big O of log base 1000 of n. So let's figure out the number of disk accesses. I'm hoping that this will be worth it. The number of disk accesses is going to be approximately the log base 1000 of 10 to the power of 10. Remember, that's 10 billion. 10 billion. 10 billion. This is going to be, if you calculate this out, this is approximately 3. This is significantly better. So I'm going to give you my final theorem for the class, and then we'll stop, okay? So I'm going to give you my final theorem that encapsulates what I've just described here. So do you see how much, in terms of the lessening of the disk transfers or memory accesses that I need for the B tree, I have control over this using D appropriately, which is, it's rather kind of wild. So let me give you the final theorem, and I'm hoping you'll spell out the answer why I call this a B tree, possibly. Because there's actually debate about why you call it a B tree. I'm hoping I'm going to posit some idea to you why maybe it might be interesting to call it a B tree. So let me quickly write out this theorem. I know I'm a little bit over here, so I apologize for that. But I hope it will be worth this theorem. So here we go. Here's the final theorem. Final theorem. Let capital B denote the number of elements that fit into a block which it's block size. So this is something that's actually system specific. So it's block size. So a B tree, rather interesting, it's a capital B, right? A B tree with n records performs big O of log base capital B n disk accesses for retrieval or update operations. So one of the speculated reasons why people think of B tree and why it's called that is they think it means block. Some people believe it means block. So you might ask, why should we care about B trees? Well, I'll tell you quickly. So this theorem gives you a very interesting framework to work with if you're thinking more about external memory. So B trees can be further specialized to obtain data structures such as B plus trees, which appear commonly in file systems and relational database management systems. Boom, right? So you thought this was going to be a course about data structures and algorithms. I thought I would kind of finish off with the grand poobah if you think of data. So that being said, I want to say thank you very much. I want to apologize for the extra time I've used here tonight. And I want to say thank you very much for everything this term. It was a pleasure to have everybody this term. And keep an eye out for the exam format. It'll be coming out the next day or two. So I'll say thank you very much for everything this term. So thank you for the honor of being your professor. It's always a great opportunity to be with lovely, lovely students. And I'll say thank you and have yourself a beautiful evening. I'll see you later.